Well, here we go again. Last time we learned a little bit about molecular geometry, and we said, hey, if we could figure out bonding domains and non-bonding domains, we could use a chart to predict the shape of the molecule. And what did we say bonding domains were? Well, we said these are atoms directly bonded to the central atom, right? So if we look at something like our acetic acid, which is CHHHO, oops, CHCOOH, and we say we want to know the geometry around this atom. How many atoms are directly bonded? Well, there's one atom, there's two atoms, there's three atoms. What about all of these over here? They don't count because we're only talking about this carbon because it is directly bonded. So we'd say, hey, there's 1, 2, 3, 4. And we'd say there's 4 bonding domains. Good. And then what are my non-bonding domains? They are what? Electron pairs on central atom, which are not shared or unshared electron pairs. So if we look at, for instance, this oxygen here, we say, okay, there's a hydrogen here and oxygen there. So we'd say that it has 2 bonding domains, but we also have an unshared pair here and an unshared pair there of electrons. So we'd say it has 2 non-bonding domains, okay? And then based on that, we could use a chart, which we've all memorized by now, where we look at bonding domains and non-bonding domains, and we can get the molecular geometry. Perfect. So now we want to go further, and we want to consider this. Consider nitrogen, bromine pentafluoride, and boron trifluoride. Which of these molecules is symmetric in shape? Egad, so we have to figure out symmetric in shape. Well, how do we do that? Let us write down here symmetry. Good. So we want to talk about symmetry, and we want to talk about what is symmetric and what is asymmetric. I hope I spell symmetric and asymmetric right. Egads, what if I don't? I'll be in trouble with my math and English teachers. Let's start here and let's just look a little bit. Linear. Do you think linear is symmetric or asymmetric? Well, linear turns out to be symmetric. What about trigonal planar? If we think of that in 2 dimensions, that turns out to be symmetric as well. What about if we look at bent? And remember, we're only looking at the atoms, not the unshared pair here. Does that look symmetric in 3 dimensions? The answer is no. It is asymmetric. Tetrahedral is symmetric. Trigonal pyramidal. Okay, trigonal pyramidal. Notice that on one direction here I have this unshared pair, then I have 3 atoms all kind of below the main atom A. This would be asymmetric. Bent again, asymmetric. My trigonal bipyramidal. Hey, this is a beautifully symmetric shape. Seesaw, asymmetric. T-shaped. T-shaped turns out to be, hey, everything on this side looks symmetric. What about on this side? No, it is asymmetric. Linear is always symmetric. Octahedral, symmetric. Square pyramidal. Hey, I have an atom up here, but I have an unshared pair down there. That makes that asymmetric. And finally, square planar. Square planar, unshared pair on top, but it's offset by an unshared pair there. My atoms are around, so that is symmetric. Good. So let's add some shapes here. Linear, that is symmetric. Trigonal planar, that is symmetric. Tetrahedral, that is symmetric. Let's see what else. Trigonal bipyramidal, that is symmetric. Octahedral, symmetric and square planar which will leave what? Bent trigonal pyramidal. Let's see, what else? Seesaw, T-shaped. What's next? How about my square pyramidal? Have I covered all those? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11, let's see. 1, 2, 3, 4, 5, 5, 6, 7, 8, 9, 10, 11, 12, 13. Let's see. What do I have here? Square planar, yes. Square pyramidal, yes. Octahedral, yes. Linear, we've covered. T-shaped, seesaw, trigonal, bipyramidal, yes. Bent, yes. We have a couple bents, yes. Okay, I think we have them all. Good. So that's how we tell. We just have to kind of memorize this, guys. All right? Good. So let's figure this out. Nitrogen is what? Well, anytime you have two atoms, it is linear, meaning this is symmetric in shape. Bromine tetrafluoride, what do I have here? I have 7 and 35. I need 42, which means it looks like this, I believe, right? And we put our unshared pairs around. Good. And what kind of shape do I have here? This is seesaw. And if it's seesaw, this is asymmetric. Hey, I hope I'm right on this. Should we go back and check? Let's see. Oops. Let's see. That's not it either. How about here? There we go. Oh, nope, it's 5-1. I can't add 5-1. It's square pyramidal. Square pyramidal? That's not square pyramidal. Yes, it is. Sorry. Zoink. 5-1. I left off. There we go. That's not seesaw. Yoink. Square pyramidal. Egads. And it is still, square pyramidal is asymmetric. Well, at least I got that right. And finally, boron trifluoride. Remember, boron's one of those interesting guys who only wants 6 valence electrons instead of 8. And so what is this? This is a 3-0, meaning it is trigonal planar. And if it's trigonal planar, it is symmetric. Good. All right. That's how easy this is. You guys pause me and you do these 3 or 4. Okay. Well, here we go. What did you do? Let's look at ammonia. I know ammonia well. It looks like this. It is a what? 1, 2, 3, 3, 1. That is trigonal pyramidal. And if it's trigonal pyramidal, it is pyramidal. It is what? Asymmetric in shape. What about CH4? CH4, that is a 4-0. That means it is what? Tetrahedral, and tetrahedral is symmetric. Good. What about CH3Cl? CHHHCl. Once again, that is what? That's a 4-0. 4-0. So it is a tetrahedral in shape, right? And so that means it is symmetric. The shape is symmetric. It has a symmetric shape. And you notice I am emphasizing shape here, which means, hey, I'm going to drop another shoe in a few minutes, right? Good. And when we go up here, what's the last one? Selenium tetrabromide. Okay, I finally have my selenium tetrabromide. And so selenium is a 6 plus 28. Looks like 34 to me, right? Valence electrons. 1, 2, 3, 4. Complete my octet. And what is that? 8, 16, 24, 32, 33, 34. There is my seesaw. That's a 1, 2, 3, 4, 1 seesaw. Seesaw is what? Asymmetric in shape. Egads. Good. Do you think I did that right? I hope so. Let's see. Did I do it right? Oh, it's not on here. Okay. Good. Let's move forward then. I'm assuming I'm right. Yeah, I'm pretty confident I'm right. Because when I add up my electrons, that looks good. Here we go. Next question. Consider carbon tetrachloride. Is the CCl a polar bond? Is the carbon tetrachloride a polar bond? Do you remember anything about polar bonds? Oh, yeah, I do remember some stuff about polar bonds. All right, now here's what we get. Out of our symmetry, we get this discussion of molecular polarity. Polarity. And we don't want to confuse this with bond polarity. Do not confuse. So what is bond polarity? Well, bond polarity is what we did long ago in another lecture where we looked at the delta electronegativity. Remember we said, oh, yeah, that's right. If this delta is 0, that is a non-polar what? Bond. Oh, and if it's greater than 0, if the difference in electronegativity, not less than, yoink, greater than 0, then we said, hey, it's a polar bond. And if it's very, very polar, we say that it is ionic. But this all has to do with what we'd say is uneven electron distribution in a bond. Okay, or if we say electron or electrical, I'll accept both of those. Uneven electrical distribution in a bond, whereas what is molecular polarity? I think we could figure this out. Not definition. How about definition? Definition. Eeks. Definition. Here we go. What's the definition of molecular polarity? It is an uneven distribution. What kind of distribution? Uneven electron distribution in a molecule. Good. And if we have this, we call this a polar molecule. And another word for a polar molecule, aka, is a dipole. Good. So now, how do I determine? What's the process for determining molecular polarity? Now, the way I like to do this is I like to use a logic tree, I guess. I use a logic tree to figure this out, meaning I'm going to place a question and then place some other questions, and that'll give me the answer. So here's how I would do this. The first question is shape symmetric? Aha, now you understand why we ask about symmetry of shapes. If the answer is yes, then we have another question. If the answer is no, if it is not symmetric, meaning it is asymmetric, if it is asymmetric, then my polarity is polar. Then you have a polar molecule. So anytime you have what? Trigonal, pyramidal, seesaw, square, pyramidal, all of those are always polar molecules. Good. What if my shape is symmetric? Well, then we have to place another question. Here it is. Is central atom surrounded by atoms with same electronegativity? And what that for us means most of the time, do we have the same atom surrounding my central atom. So if we have something like HH, right? HH, this is linear, so it is symmetric. I have the same atoms on both sides, so this would be, if the answer is yes, then that would be non-polar molecule, meaning I have an even distribution of electrons in the molecule. But let's say I have something like HCl. Okay, this is a linear shape, but notice my Cl and my H are not the same. So this answer is no, and these have different electronegativities. So this is what we'd call a polar molecule. All right? So that's it. Just memorize this logic tree, and that'll take care of, 90% of the questions related to molecular polarity and 100% related to molecular polarity in our class. So what's considered carbon tetrachloride? Here's my carbon tetrachloride. The first question is, here's my chlorine and here's my carbon. Is this a polar bond? How would I find that? I have to look at my electronegativities and, oh no, where are our electronegativities? Well, I have to pull it out of my head. And chlorine is a 3O, carbon is a 2,5. They're not the same, so that means my bond is what? This is a polar bond. And that means what? I have an uneven electrical distribution in my bond here. And really, what would this mean? This has a stronger pull on the electrons than this. So in my bond, my shared electrons would be closer to my chlorine than they are to my carbon. But what about my carbon tetrachloride? Well, first thing we have to look at is polarity. No, excuse me, polarity, symmetry. This is a 4-0. It's a tetrahedral. Tetrahedral is symmetric. Good. Next question. Do I have the same atom around my carbon? And the answer is yes. So this is symmetric shape, and I have the same atoms around. Yeah, they have the same electronegativity, right? Same atoms surrounding my central atom, and so what do we conclude? This is a non-polar molecule, which kind of points out an interesting thing. I can have a non-polar molecule with 4 polar bonds in it. Got it? Okay, cool. Here you go. You try this one. Freeze me and bring me back when you're ready. All right. Nitrogen, and we have these pictures already here, right? Here's my nitrogen. It is linear. I have the same thing on both sides, so this is what? Non-polar. Next, bromine. Let's get this right. Finally, pentafluoride. Yes, I think I can finally get pentafluoride correct. Pentafluoride. 1, 2, 3, 4, 5. I have it. 2, 4, 6, 8. There we go. And we would say, let's make sure 5 times 7 is 35, and 7 is 42. 8, 16, 24, 32, 40, 42. This is trigonal, not trigonal. It is square pyramidal, right? Pyramidal. Square pyramidal, that is asymmetric. If it is asymmetric, then it is what? A polar molecule. Non-polar molecule and a polar molecule. Good. And then finally, we have my boron trifluoride, right? And we said the shape of this was trigonal planar, and we all know that trigonal planar is symmetric. Do I have the same atoms surrounding my central atom? Do they have the same electronegativities? Yes, so this would be a non-polar molecule. Okay, great. All right, let's try these. Give this a shot, and I'll give you a hint. There's a trick here. Go. Bring me back. Here I am. Ammonia, I think that's not a trick. I think that one's pretty easy, right? We say what? That's O3-1. It is trigonopyramidal. If it's trigonopyramidal, then it is asymmetric and it is a polar molecule. Good. Carbon tetrachloride, or not carbon tetrachloride, this is methane. Methane looks like a 4-0. That means it's tetrahedral. I have the same atoms surrounding it, so this is a non-polar molecule. Wunderbar. Good. What about this thing? CHCl3. You know what? I think I drew that wrong last time. CHCl3. I think I drew CH3Cl. In any case, here we go. What is this? This looks like a 4-0. It's tetrahedral, and you're going to say it's nonpolar because it's symmetric, right? No. Notice I have a chlorine, a chlorine, a chlorine, and then a big hydrogen here, meaning my central atom is not surrounded by these same atoms. If it's not surrounded by the same atoms, it's not surrounded by atoms with the same electronegativity, I should say, then it is going to be a polar molecule. And why is that? Well, this has a 2-5 electronegativity. This has a 2-1. This has a 3-0. So that would mean what? My chlorines are all pulling on the electrons more than my hydrogen. In fact, the hydrogen's not pulling on them very much at all. So where my chlorines are would have more electrons, and this thing would have what we call a partial negative. And the area where my hydrogen is would have a partial positive. You don't have to worry about the partial negatives or the partial positives. Just wanted to show you that. And finally, selenium tetrabromide. Good. Selenium tetrabromide. Here's my selenium tetrabromide. Here's a bromine, and here's a bromine, and here's a bromine, and here's a bromine. And I complete my octets. And what is that? That is what? 8, 16, 24, 32. But how many do I need? I need 34. So he said that that was seesaw. If it's a seesaw, that is asymmetric. If it's asymmetric, that means it is a polar molecule. Okay, great. That is our answer. Okay? Let's see, where did I make my mistake? Let me fix that before we go on. That's not it. There it is. Sorry, folks. We'll come down here and finish this right. That needs to be a chlorine, and that needs to be a chlorine, right? Sorry. Okay, there we go. That is it for today. If you have questions, let me know. See you next time.